All right, well, welcome. What I'm going to do today is get going on a video that's going to do a little bit more on the PV that we worked on before break, and then in addition, get us going on water heating. So we talked a little bit about water heating, and I want you to be able to consider three options and do an analysis. Say like for a client, which option makes sense in this case? So, and one of them is going to be using the PV. For sure. So we're going to go ahead and get back at it, and I'll talk more about details on finishing off the semester or the rest of the semester at another time. So what we talked about earlier, just a quick review. PV cell, we thought about two different layers of materials, okay? And a lot of times there's wire leads connected to it so that we can hook up some sort of load, and we're thinking about sunlight coming in, okay? And then the sunlight has a different impact on the two different materials where we end up getting a charge separation like this and like that. And so we're looking kind of like a battery, or we're looking like a source where basically if we were to connect these leads, we could get flow. All right? And what we wanted to do, maybe a great way of starting out with this is to be able to think, okay, what's this graph going to look like? Okay. Where on the y-axis we have the current that's produced, and I'm going to use I sub L for the load current, and the x-axis we're going to have what the load resistance is. The load resistance is. Okay, and so what we want to, first of all, we want to know that it's a lot different than a battery. If you had a battery, okay, you have hardly any resistance, you get a high current, and as the resistance goes higher, you get less and less current. You get something that's kind of hyperbolic, and we talked about that earlier. Okay, so a solar cell is a lot different, all right? And what's going on, actually, just graphing it, the main thing we want to do is we want to be able to think, okay, what does it mean to say that a PV cell, or a PV generator, which is the blue thing, is a constant current producer? Well, that's what the graph essentially would look like, that we end up getting, no matter what the resistance that's hooked up, we end up getting the same current going on. And a little bit later on, we're going to try to do a demonstration to show that that is basically true. Okay, so why would that be? Well, if you can go back to the photoelectric effect, that's going to kind of give you a sense of what's going on. So with the photoelectric effect, we had some sort of material, and we had energy coming in, thermal radiation coming in. Could be from anything, a laser, a hot piece of metal, the sun, etc. And what we got is that we would end up getting some electrons actually ejected off. We get some electrons ejected off. And in a sense, the number of electrons that get ejected would depend on the intensity of this energy. Okay? So basically, we can think of this sun right here, in this case, as interacting with the PV panel, which is basically two different PV materials, one on top of the other, in a similar way. If we're at a certain intensity, like 1,000 watts per meter squared, we have a certain number of electrons are ready to go. And those electrons want to go from here to here, regardless of what the resistance is. So if I hook up a very, very small resistance, I get a certain current. If I hook up a larger resistance, I'm going to get the same current. A larger resistance, the same current. The larger the resistance, the same current. Okay? It is true that if we hook up a really, really large resistance, if we get somewhere way out here like this, that actually we're going to get 0 ohms. And so in theory, we might get something like that. Okay, now that's not exactly right, but the main point I want you to be able to think about is, hey, let's think about a PV generator at a certain solar G, 200 watts per meter squared, 400 watts per meter squared, 1,000 watts per meter squared. At that G, it's going to generate a certain amount of current flow regardless of the resistance that's hooked up. All right, so that's our starting point. So let's go outside and take a couple resistors out there. I'm going to take this resistor out there, and I got a couple other things outside. We're going to hook them up to a PV panel and see how the resistance changes. How the flow changes with resistance. Do we get the same current regardless of the resistance we hook up? Basically, as we talked about before, this is that real small PV panel that I got. And the way we thought about it in class is, even though it's not a sunny day right now, there is solar hitting this surface, and as a consequence, we've got charge here ready to flow from there to there. So if I could do some sort of connection between in here, and here, we're going to get a loop of charge. And let's just take a look at how the theory works. Again, as we were talking about earlier, this represents the PV panel, this represents the sun, this charge is ready to move as long as I complete the circuit, and what we're wondering is if we vary this resistance, what kind of current are we going to get? So we're going to go ahead and check it out. We're going to start with the resistance of 0, so that's going to be a short circuit. So to do that, what I'm going to do is I have a lead here, and I'm going to actually connect it to the wire coming out. And so that current's going to run here, and it's going to run through the current meter, and then it's going to come on back over here like this. Give me a second to hook this up. And now we got a complete circuit coming out of the panel, going through the ohm meter, and then coming back in. So that's just simply wire right here. Resistance is 0. And what kind of current are we getting? Okay, not good. This thing should be able to produce pretty close to 2 amps, a bit under 2 amps, and it's doing about 0.28 amps. Okay, we can change it. We can change that pretty easily. If I just go ahead and shade the collector a little bit, I'm getting less and less, and I'm just going to go ahead and stand in front of it and see if I can get it down to a pretty low. Okay, pretty low. So I'm blocking a lot of the sun, but there is that diffuse that we're talking about that's coming over here, and coming over here, we're still getting some current. Okay, but back to our full panel. So we're getting about 2.27 amps, 0.28 amps. All right, we're gonna go ahead and hook up another resistor to it. So what I'm gonna end up doing, is I got this ohm resistor here. We talked about that last time we met. That's a 5 ohm resistor. It's a pretty low resistance actually. And I'm gonna go ahead and hook that up. So now instead, pardon me, we've got 5 ohms going through there. Okay, I touch here and I got short circuit. And it looks like we're up to about 0.3 amps. Maybe there's a little bit less clouds right now. And then now I'm going through the resistor, 0.32. Virtually the same current. So what we got so far, then what this graph would look like, if I were trying to do this experiment and be detailed, we've got a certain current when the resistance is 0, and then we went up to 5 ohms, and we got the same current. We got the same current. Now my dot's not really well, bear with me because I'm graphing upside down. Let's do another resistance. Let's do another resistance and see how that works out. Okay. So I'm going to disconnect this right here, and I'm going to go with a piece of rubber. So we had a piece of rubber and we talked about that. I sort of talked you through that on the test 1. By the way, more on test 1 soon. But right now we're just going to focus on material. Okay, that was supposed to be a high resistance. So I'm going to go ahead and do the short circuit, 0.3 amps, and then going through that rubber, 0 amps. So now we got another data point, okay? If we have an incredibly large resistance, so if we're way over here, somewhere way over here, we would get 0 current. So 3 pieces of data. What about somewhere in between? What about somewhere in between? Well, unfortunately, I got this lamp here. Hopefully you can see it off in the distance. Let's just go ahead and get its resistance really quickly. Assuming this numbers are approximately right, it's a 12-volt bulb, and it's supposed to produce 20 watts. 12-volt bulb, 20 watts. So if we hook that up to 12 volts, we'll get 20 watts. A light bulb's basically a resistor. So let's just, if you could, maybe you could just write that down and pause the video and see if you can work out the resistance. I'll be doing it myself. Just make power equal to 20 watts and voltage equal to 12 volts. What's the resistance? Okay, so here's the math. You know, for a straight DC circuit, the heat dissipation or the power production is the current times the voltage, and that current is V over R, so I got V squared over R. In other words, power is V squared over R. Do a little bit of rearrangement and you get the resistance is the voltage squared over the power. So we ought to be able to do that on our calculator. We had 12 volts and we had a power of 20 watts. So let's just take a look at that really quickly. 12 volts and 20 watts. I'm just going to pull out my calculator and do that. See if I got what you guys got. So I'm going to do 12 squared divided by 20 Okay, and I got that that's a 7.2 ohm resistor. So a slightly different resistor. So I'm going to go ahead and put that up there. Get the rubber out of there. Okay, and I'm going to try to hook it up to the PV panel. And I got all this wiring, which is just extra stuff. Okay, so first thing I'm going to do is try to do short circuit, and let's see if we get any current short circuit. So about 0.3 amps. About 0.3 amps. Okay, now I'm going to try to go through the light bulb. Try not to cut myself. Unfortunately, this got shattered, but that's okay. Okay, and hopefully you saw, I'll get that up there again, hopefully you saw that you got about the same amperage. So once again, a different resistance and you end up getting the same amperage. Okay, so then I'd have another point here like this. And ideally, if we had an experiment, we could do a bunch of different resistances. We're going to get the same current. We're going to get the same current until the resistance gets really large, until the resistance gets way out here like this. So as I was talking about earlier, a great way to think of a PV generator, like this generator, is a constant current producer given a certain level of radiation coming in. All right, so we'll get back to work on that in just a minute. But first, while we're out here, I just want to talk about water heating just a minute. As I've talked about in class, water heating is a huge source of energy use. And let's just do a quick demo on that, or just a visual on that. So this amount of water here, what kind of energy would it take to heat it up? We've got over the equation, review it quickly. What about method? One method that we talked about was putting this in a black box, and the sun's going to hit the black box, and that black is going to get really warm. The heat is going to go into the water. How about this alternative here? We got a PV panel. How are you going to go about doing that? So bear with me for just a second. Okay. So I'd like you guys to be able to consider all you guys to be able to consider the option of using this. Okay. If we hook this up to a PV panel, this is a resistor. It's going to change electrical potential energy into heat, and then by putting that heat in contact with water, we can actually get the water to warm up. So just going through that really quickly. I'm going to disconnect the ohm meter. Okay. I'm going to connect this PV cell right here like this. Bear with me for just a second. Okay. So it would be great if I had some sort of temperature gauge on this, but I can actually feel this thing warming up. So the sunlight's actually hitting that cell, and then we're creating current. The current is going through the resistor, and the resistor is actually warming up. Okay, so what we can just do simply, just bear with me while I do this, okay, is we actually can just put that resistor in water, okay? And you can't, unfortunately, it would take quite a while for us to get that water up to 125 or some sort of temperature that would be serviceable. I'm doing a job right now where they're trying to get the water up to 190 to do sterilization. It would take a while to show it, but what I just described is exactly what's going on. We've got solar energy hitting here. It's putting that energy into electrons essentially, which flow across here like this, and then the resistor is taking that electrical energy and turning it into heat, and we get a continuous cycle with heating. So a little bit later on in the lecture today, we'll evaluate that. How's that going to work out? How effective is it going to be to take the PV panel and make energy to put in the water versus using the black box and take energy and put it into water? All right?
Okay, go ahead.
All right, so with a bit more sun, how much current are we going to get? Let's just go ahead and try that out. Try to be quick and get that up there. So I want to take this lead over here. Bear with me for just a second. And I want to go through the ohm meter. Okay. And then I want to come back through and complete a circuit. So I'm going to complete a circuit, and hopefully we'll get some sort of current flowing. So a little bit better because there's a little bit more sun right now. And then if I were to actually instead go through the resistor, so through the resistor about 0.7, and then if we short circuit, about 0.7. Back through the resistor, 0.8, short circuit, 0.9,
sun's really varying right now, but we're getting the same current short circuit versus through the resistor, almost.
So the next thing to do is to understand, hey, why does the graph look that way? A little bit more detail on that. Why do we get a constant current given a certain resistance? And then once the resistance builds up to a certain point. So thinking about a current splitter is a really good approach to do it. We talked about that briefly before break, and let's do some more on it really quickly. So a current splitter would be the idea that we have some sort of current source, and a PV panel is a current source. Okay, and we actually have two different resistances that can go through, an R1 and an R2. So how do we go through and work out how those numbers work? Say, given that we had a certain current, 10 amps, how is it going to split? Simple idea, most of the current is going to go the path of least resistance. So if this resistance here is low and this resistance here is high, most of it will take this path here like that. But actually mathematically working it out, well, there's a couple ideas you need to have. I mean, first of all, if we end up calling this current here, the first current going through resistor 1, I1, and the second current here, I2, then it's going to be true that I1 plus I2 has got to be equal to I. Okay, so that's a useful relationship for current splitter options. All right. The second idea basically is that we have current here that has energy, and the current that goes through here loses a certain energy per coulomb, and the current going this way loses a certain energy per coulomb. Energy loss per coulomb is delta V, okay? And so if we did delta V1 as the loss through resistance 1, in most physics textbook it's abbreviated as V1, okay? That is actually going to be equal to V2. All right, so you can combine this first equation with this idea and Ohm's law to get a relationship that's really useful. So let's go ahead and write that. Let me write that down and we'll get going on that. I'm going to try to switch sides so that my hand doesn't block the board. So give me just a second. I don't know if I can do that. Okay, so there we go. All right, well, actually, I think I'll just turn it to me and write really quickly and see if that makes sense. So basically, you've got I1 is equal to V1 R1, okay, and I2 is equal to V2 over R2, okay. Those are a couple of relationships that we have, all right, and then since we know the voltages are the same, we can actually say that V1 is equal to V2, and so we can say that I1 R1 is equal to I2 R2. Let me get that up there. That has to be true for a current splitter. I1 R1 is equal to I2 R2. Okay, and then we can get a useful relationship if we solve that for I2. I2 is equal to I1 over R2, and then we're almost there to actually have a useful relationship that allows us to go through and do some typical problem solving. Bear with me for just a second. Okay, so we end up getting this relationship here is that I1 and this quantity right over here, pardon me, this quantity over here is I2 is going to be equal to the total I. And that can be a useful relationship for doing some problem solving if you have a current splitter and you're trying to figure out how the current's going to split. All right, so bear with me for a second while I erase the board and I'm going to get an example up there. For the rest of the semester, either with this whiteboard or maybe I can find something larger that I can use with you guys. I'm going to do some examples, and I think a key part of making this work for you guys is just similar to class. In similar to class, I try to pause and give you guys a little bit of time to do a little bit of work. Here I'm going to try to pause as well and give you guys this time to do a little bit of work. So let's get that example up there, and I'll read it out loud. You can start writing it down. So we've got a current splitter, okay, and we got some sort of source, and let's just imagine it's a really large PV panel that can do 10 amps, much larger than we had outside. Okay, and let's see if we can hook it up to two resistors. R1 is equal to 6 ohms, and R2 is equal to 4 ohms. Pardon me, 2 ohms. Okay. So if you, ideally what you'd do is do a little bit of a drawing. So you got this first resistance of 6 ohms, second resistance of 2 ohms, and you've got 10 amps coming along. Okay, so there we go. So how is that going to end up splitting? How's that going to end up splitting? So again, I encourage you to pause the video and see if you can use the last equation I wrote on the board or something similar to it to go through and work out what the two different, what the split is. What is the split among the 6 and the 2? I'm going to be doing it myself. When you come back, you can probably fast forward through this part of the video because it's going to take me a second to do the problem solving. Okay, so again on the problem solving, I encourage you to pause the video and get as much as you can on your own. If you get stuck, run through the first portion of the video and get the next step and then take it from there. The more work you think through on your own, the better this is going to be. So again, I'm trying to get this 10 amps and figuring out how it splits between the 6 ohm and the 2 ohm resistor. And I'm going to get started on getting the equations up there. Okay, so there's a first step. We know I1 plus I2 has to be equal to 10. In addition, because we know the voltage drops are across those resistors that are the same, we can write R2 as R1 I1 over R2. And so I got this equation here, which is either identical or equivalent to the equation I wrote at the bottom of the board a little bit earlier. And we can solve that. So the goal here is now to solve that equation for R1. If you need my help to get to here, no problem. But see if you can take it from here and finish it off. Okay, so there's the next step. I1 plus R2 over R1 times I1 is equal to 10. And we ought to be able to take it from there. Okay, so I got I1 is 2.5 amps. I2, how are we going to get that? Well, sorry about this little smudge up here, but I've got 10 amps coming along, and I knew that I actually ended up having 2.5 amps going that way. 7.5 amps has to go that way. So that's some good problem solving. Okay. All right. And it should all check out. It should all check out. We've got more current going through the path of least resistance. The voltage across both resistors are the same, and that works out well. Okay, this one I really think you should be able to take away all the way through yourself. So in this case, we're going to make R1 6 ohms, but we're going to up R2, and we're going to make R2 equals 54 ohms. So I'll get that statement up there. Give me just a second. And then again, do your best to take it through the whole way yourself. Okay. So there's the problem statement. Okay. 10 amps over here. 10 amps coming. How's it going to split? This one's 6 ohms, but now this one over here is 54 ohms. Okay. So hopefully we have more current going this way because that's less resistance, and we're going to try to use the same equations. All right. This time I'm going to go through the whole thing myself and then get it back up there and take a look and see if it makes sense to you. All right, well, I got that 9 amps went through the 6 ohm resistor and 1 amp went through the other resistor. So here's the work. Really same little exact same problem with different numbers, but a little bit of a lesson there. So same equations, and then I did R1 over R2, 6 over 54. That reduces to 1/9. And so then from there it's just algebra, and I got I1 is equal to 9 amps and I2 is equal to 1 amp. All right. So what hopefully, it just makes sense now with this current splitter. The larger we make this second resistance out here, or the one particular resistance, the more current goes to the other resistor. And there's a mathematics behind it so that we can solve it and work it out exactly. Okay, what does that have to do with PV? And we talked about it in class, and then on the test I gave you a drawing to help you make a little bit more sense of it. But what that allows us to do is flesh out a little bit more what's going on with the PV, with the idea that a PV cell is a constant current producer, but there's 2 different ways the electricity can go. So bear with me while I get a quick drawing up there. All right, so drawing similar to what's in the book, but with a little bit of variance, and certainly similar to what we had on the test, where we can have current go through this load, but there's actually a way for this charge. Let's take a look at like one particular charge element, and there'd be a corresponding plus down below. There's actually a way for that current to go through the PV cell and go that way like that. And that's resisted by what's sometimes called the shunt resistance. So there's 2 different paths, and if you think about it, those paths are in parallel. And this way of drawing it makes it a little bit more dramatic. This shunt resistance is pretty large, so usually the current goes through the load. But as the load gets larger and larger and larger, we start getting current through the shunt resistance, and sometimes that becomes significant. And that then is why you get a characteristic current graph like those are seen in the book. So let me just go ahead and just do one graph really quickly, not what's seen in the book. So bear with me. So I got this axis right here is current. Okay, and if this axis here were resistance, then we're going to get, at 0 resistance, we're going to get a certain current. Okay, if these 2 leads touch each other, we're going to get a certain current, and that's just going to be constant. If we add some resistance, the same current, add some more resistance, the same current, add some more resistance, the same current. And then as this resistance here gets larger, some of the current's going to start going that way, and we're going to get a fall off in I load, the current that actually ends up going that way. All right, for various reasons. First of all, I should say that that's an incomplete picture of it. And I asked you on homework number 6 to go through and take a look at a more detailed view of a solar cell. Not that I'm going to hold you responsible for it, but I want you to know that this is a pretty incomplete model, not a bad model. Okay, how actually then is the characteristic of a PV cell represented? And we've started working on that. Instead, what we have is voltage, and that is load voltage, and this is load current. That's what those graphs look like. Okay, and if you think about it, what would happen then if we had a certain resistance here and we had a certain current going through there? We would get a certain voltage, and I could put that right there as that voltage right there, and we're going to get a certain current. And then if we double this resistance, same current, the voltage should double, and we're going to get another dot like that. Triple the resistance, you're going to get triple the voltage, and you're going to get a dot like that. Okay, and then at some point, the voltage ends up, the current over here gets large enough that the external current starts falling, and you get a characteristic graph like that. And that's what you'll see if you go online, or if you get specs from some sort of equipment supplier, they're going to give the graph like that. The book does a better job of representing the fact that if you have a little bit of resistance, the current external resistance, you start getting some flow in the other direction. So basically what the book does when they characterize it is they're going to put a current right here, and that's called ISC for the short circuit current. So you're going to see a dot like that in the textbook. Okay. And then if we hook up if we actually just touch these two leads together, that would be that value right there. And then if we put a small resistance in there, we're going to get virtually the same current, but it's going to be a tiny little bit less, because a little bit's going to go over this way, and then a tiny bit less, and then a tiny bit less, and a tiny bit less. So instead of that straight line, the book has a slight downward slope, and then we build it to some sort of resistance and it really falls off. And then when we get a very, very large resistance, which would be equivalent to an open circuit, then we end up getting zero current at all. And so over here we have V with the subscript OC, and that represents open circuit current. Okay, good. All right. So we want to be able to do a little bit of problem solving with that, and made it real easy on the test. Please don't feel badly if that didn't go so great for you, but want to give you another shot at that on homework number 6 and then on quiz 2 as well. So let me get an example up there and get you to work. So, but in short, you can go ahead and get started. We're going to imagine that we have some specs for a PV cell, a PV generator, and the specs say, look, at full sun, this open current voltage is 20 volts, and then the short circuit current is 2 amps. So, and that's at full sun, which is 1,000 watts per meter squared. So I just want you to go ahead and graph, and I'd like you to graph it more the way that the manufacturers give those. So we're going to try to do a graph like that. Once again, VOC, 20 volts, ISC, 2 amps. Okay, so here is a complete cryptic problem statement. We have a PV generator that at full sun has VOC of 20 volts, ISC of 2 amps. We want to graph it at full sun, 1,000 watts per meter squared. The typical graph where we have voltage on the, probably current on the y-axis and voltage on the x-axis. And then I want you to figure out at 2 ohms, how's that going to operate? How's that? And you would want to do things like figure out the current, and you'd want to figure out the voltage for the load, and you'd want to figure out the power for the load. So 3 things: current for the load, voltage for the load, power for the load. Okay, and then finally, let's do that for 4 ohms. So I'm going to go through this one slowly and then have you do that one. So you can go ahead and pause the video if you want to. First thing to do is the graph. Okay, well there's the graph. It shows that basically that we end up getting a constant current no matter what resistance we hook up to it, and the resistance is going to correspond to the voltage. And then at some point the resistance gets large enough that that current starts falling off. And if we have an open circuit, we're going to read 20 volts across the leads for the PV panel, and we're going to have 0 current. So that is typically what's given by a manufacturer. This point right here, this circle, would be the maximum power point, and more on that later. Okay, let's just go ahead and imagine then that let's start with the 2 ohm resistor. What if we have a 2 ohm resistor? So I'm going to get some work up from there. Again, your goals are to get current through the 2 ohm resistor, voltage across the 2 ohm resistor, and then power. So I'm going to try that really quickly. All right, so how do you go about doing that? Well, I think the first thing to do is to try to decide, hey, where are we on this graph? Is 2 ohms going to be a really, really large resistance that's going to put us over in this region over here? Or is it a pretty small resistance and putting over there? So the way I approached it is I said, hey, could there be 2 amps going through there? Could there be 2 amps? Could we be in that region over there? So I'm going to calculate, what I can do is I can calculate the voltage across it here if there were 2 amps going through it. And that's IR, and 2 times 2 is 4, so I get 4 volts. Okay, so what if we were at 4 volts here? This graph tells us how the PV cell is performing. So I read up there, 4 volts, and I end up getting 2 amps. So that is in fact correct. If we have a situation where we had a 2 ohm resistor, we would be in this constant current range. All right, so now we're almost there. We've got the current, we've got the voltage, and what about the power? Okay, well, the power would be the current times the voltage, and I want to get that number up there. So the current is 2, the voltage is 4, and we're going to get 8 watts produced by this circuit right here, 8 watts. All right, let's try it again. Go ahead and change it to 4 ohms and see if you can take it through yourself. What if we actually went over to 4 ohms? Where would we be on that graph? Okay, so once again, I just did it by guessing at it and saying, well, what if we were over here? What if we were still in this 2 amp range here like this? Is it going to work out? So I calculated the voltage, and the voltage would be 2 amps times 4 ohms. That's 8 volts. Okay, this is 20, way over here where things fall. And the fall occurs near 20, maybe about like 17 or 18. But we're instead way over here at 8 volts. So yeah, we're still going to have 2 amps. We're still going to have 2 amps going through that. And so I can go through to the calculations. I got 8 volts, I got 2 amps, and I got 16 watts. And that's the key thing that I want you guys to work on homework some more, or just thinking about it or looking at the reading. You can see that the power you get out of a PV cell depends on the resistance you hook up. And so over here, we're getting more power than we did at that first point like that. And as you keep going to the right, you keep getting more voltage and more voltage. That's more joules of energy per coulomb. And then and right around here, when the current first starts to drop off, that power maximizes. So this right here is IMP, the current of the maximum power point, and this is also VMP right there. So there's a single point where you get the maximum power, and you get a current associated with the maximum power and a voltage associated with the maximum power. Okay, really good. So that gives us an idea of PV cell performance. I'm going to ask you to do some more work on that on homework. And then what if we went in a different direction now? Or what if we then said, look, maybe we can make it all work. Maybe we can find the resistor that provides the perfect amount of power, find the resistance that provides the maximum power, and take that resistor and just put it in water. That may seem like a dangerous thing to do, and you guys know that there's some precautions you need to take care of with current and water, but it's safely done in an electric water heater. So there are electric water heaters all over the place that basically have a resistor inside it, and that is hooked up to wiring. Could we take these leads and just hook it up to PV panel, and how's that going to work for water heating? Okay, so water heating, how are we going to end up doing that? So we'll just work through an example and see how the numbers turn out. So let's imagine that we're like super efficient as a family. We're only going to use 20 gallons of hot water in a day, and we're going to start out with 60-degree Fahrenheit water. And this represents our PV panel that's outside in the sun. So what we want to do essentially is we want to take that resistor, put it somewhere inside there, and hook it up and make it work. Well, one of the beauties of PV compared to solar thermal with hot water is with solar thermal, you're moving the energy with pipes, whereas PV, it's just wires. So we would have a wire that comes in here and enters the tank, and then we would have some sort of resistor in the tank. It wouldn't be suspended, but I can represent it that way. And then we would have wiring that would go back outside the building and connect to this PV panel. And boom, we're going to get current going through that resistor, and that resistor is going to warm up the water, and it's going to come back, and then the current's just going to keep flowing as long as there's sun. All right, so how would we work that out and try to make sense of it? So I'm going to get some information up there. First of all, we would like to know how much solar there actually is per day, because some portion of that energy is going to end up in the water. So one way we could do it is we could go to GEISMA. If you go to GEISMA for today, it's saying actually that the length of the day today is 12 hours and 20 minutes, and that matches up with our math. We're March 24th. We're a little bit beyond March 21st. March 21st, 12 and 12, 12 hours of sundown, 12 hours sun up, and so today is 12 hours and 20 minutes. In addition, GEISMA is going to give actually how much energy there is per day on a surface, on a horizontal surface, by the way. And so the number I got from GEISMA was 4.27 kilowatt hours per meter squared. So let me get that up for you, 4.27 kilowatt hours per meter squared. All right, so we're going to do our design and say, look, let's just say we have a meter squared panel. That is significantly larger than the panel that we brought outside. This panel here like this, maybe about 4 times as large. So it's a pretty big panel, and we're going to have to pay a fair amount for that. So how's that going to work out if we had a meter squared panel and we actually tried to put the energy in there? Well, you can do the conversions yourself if you want to pause and try it out yourself and check my work. What I would encourage you to do is convert this to BTUs, because we know how to figure out energy change or temperature change of water if we have BTUs. I did that downstairs myself before I started this video, and I got 14,570 BTUs. So that's sounding pretty good. That's a lot of energy, okay? A lot of energy that's hitting that panel. All right. So some other information. What we want to do is essentially do a chain reaction where we think, okay, there's this 14,000 BTUs of energy here. How much actually gets into the electricity that comes down here like this, and how many of that BTUs that's in the electricity as electrical potential energy gets converted to heat. And those are conversion efficiencies. So we're going to just use some typical numbers to get started on assessing this. So the efficiency of PV, 15% is a really good number. And of course, if you go into PV, upping that percent is going to be a huge part of your job and thinking about how that works. Okay, how about the efficiency of an electric resistance water heater? The efficiency of electric resistance water heater. We'll go to Home Depot, and they're going to give you some astonishing numbers. They're going to say 96%, 99%, etc. And what that is telling you is the energy that's in the electricity, how much of that energy that's in the electricity actually gets out in the water. Well, it should be high, because if you insulate this wiring, it's not going to get out of the wiring, okay? It is only going to get out at places where the energy is converted into heat. Wire has minimal resistance, so only a little bit of the heat is going to go in the wiring. All the heat is going to occur right there like that. And if you have this tank well insulated, almost all the energy that's in the wire is going to get into that water. So the efficiency of electric resistance water heating, let's use 98% for our number. Okay, and then we need one more bit information, and that is, how do you figure out the delta T of some water? And you know how to do that. If you have any mass, you figure out its change in temperature by doing the change in energy going to it divided by that thing's mass multiplied by its specific heat. We can also write that as a rate formula, so I'm going to get that up there for you in just a second. Okay, so 2 fundamental equations that can be arranged in any way you want to solve for whatever you need to. One is the delta T of some sort of mass, like the water in this water heater, is the change in that water's energy level divided by the product of the water's mass and its specific heat. Specific heat of water is 1. Okay. Also, if we want to figure out the rate of change of the water, which is something really important that we'll be doing probably starting next week or maybe even the second lecture this week, we can take the rate that energy goes in divided by MC. So for today, we're going to use this equation right here. Okay. And I want you to crank your way through it. So what we're going to do, again, I'm sorry you lost it here. We got 20 gallons of water. A gallon of water is about 8.33 pounds. It starts at 60 degrees Fahrenheit. Okay. What if we have this much solar available, 14,570 BTUs? How much of that solar ends up in the water? Okay. And then what is the consequence? What is the resulting delta T of the water? So I'd encourage you to go ahead and pause the video and start getting to work. I'm going to work this out in little bits, and so you can go back to the video and see if your work is correct. Okay, so with these efficiency problems, it's kind of like a step-by-step process. So out here over the course of the day, we've got 14,570 BTUs. How much gets into actually gets into the electricity here? How much of that 14,000 gets here? I multiplied that 14,570 by 15%, and I got 2186. So about 2185.5 BTUs. Where's where does the rest of that energy go? Well, some of that energy is reflected. Not every bit of energy gets into this panel, and some of that energy becomes heat. Only about 15% of it ends up going to taking electrons and moving them in such a position that they're ready to actually go around here and deliver energy. So not so good. This 2185.5 is not so good. So of this 2185.5, how much gets to the water? That's your next step. Okay, into the water. So here I've got like 2,185. Well, this resistance is 98% efficient. So 98% of this energy ends up in the water. And so I got 2141.8 BTUs into the water. Okay, now is that going to do us any good? We were saying we had 20 gallons. And we're a family that really is incredibly efficient with hot water. More typically would be 40 gallons. But let's say if we could get by with 20 gallons, we all take 2-minute showers. We're very careful with our dishwashing, etc. Okay, so let's see how that all works out. Okay, not so good is what I got. I got that water doesn't warm up very much. So the delta T is the energy that goes into the water divided by the product of the water's mass and its specific heat. 20 gallons at 8.33 pounds per gallon is 20 times 8.33, so that's going to be, 170-ish pounds. The specific heat of water is 1 BTU per pound degree Fahrenheit. And so we work out that we get a delta T as 12.9 degrees Fahrenheit. If the water started at 60 and then we just waited all day before we actually used that water, then we would end up having about a 73 degree Fahrenheit water for a bath or shower. And 73 degree water, that's not very good for very comfortable for bathing or showering. It's really pretty darn cold. It's not very good for dishwashing. We would want to do better so that we actually sanitize our dishes. So what's wrong with this? How can we fix this up? Well, first of all, if we're going to go PV, this was 1 meter squared in this example. This was 1 meter squared. We would need to increase the meter squared that we have. So it's going to start getting pretty large. We would like a delta T more like around 70 degrees Fahrenheit, okay, or at least 60 degrees Fahrenheit. So we're going to need over 5 meters squared. And PV gets really big really quickly depending on how you use that. Okay, what are alternatives? Do we have to do PV? Well, the other alternative that we talked about, I'm just going to get the numbers up there really quickly, was we talked about putting that water in a black box. Putting that water instead in a black box with a surface that is really good at absorbing solar. So again, we had something like that, a batch collector. And so the heat's going in here like this. This top surface is some sort of surface that's good absorbing solar, okay, and we're going to get some water in there. Well, we're going to lose some heat because of convection, and there's going to be emission as well, but with some work, this would be a good senior project, you could get something that had a daily efficiency of 60%, So what would that mean? This 14,570 BTUs, 60% actually would get into the water. And then we would get the delta T. And it's going to be the same water. It's going to actually be the same water, that same 20 gallons of water. So why don't you pull out your calculator and see if you can work through it really quickly and see what delta T you got. Okay, not bad, not great, but not bad. So when I was doing the math, I said the energy that gets from the water is that 14,570 times 0.6, 60% of it, and I divided by the mass and the specific heat, and my calculator gave me a delta T of 52.5 degrees. 52.5 degrees Fahrenheit. And then if you add 60 to that, I get a water temperature of 112.5. Well, 112.5, that's actually slightly warmer than you would like for showering or for bathing. So that's not bad at all. And it's also pretty good temperature. Maybe, again, a little bit warm for hand washing would not be bad for doing the dishes. So a meter squared, there's no way it's going to do it using PV. On the other hand, if we make this box that's a meter squared, the top is a meter squared, and then we actually have the top configured so it's coated with a surface that works out well as far as absorbing solar. And in addition, we minimize convective losses and emissive losses, then we can get us a good delta T. All right, hey, there's a third option, and we'll save that for next lecture. Please feel free to email me with questions about the lecture, since we're not meeting face-to-face on this one. You don't get a chance to ask questions. So please email me your questions, and I encourage you to get going on homework number 6. More details about previous tests, upcoming quizzes and tests, etc. I'll communicate that separately in a Canvas announcement. All right, well, I hope you guys have a good rest of the day. I'm sorry this video was up late. Take care and be well.